Okay, so thanks again to Dan. I just want to add a follow-up comment. I mean, we have been working with Dan and his team for so many years now. These machines are getting complicated. I mean, many people don't know. I mean, if you not just in the size, every cluster is different. It's like somebody is using a 2.7 gigahertz cascade lake, somebody is using 2.4 gigahertz. Switches are different, the topology is different. Optimizing an MPI stack is becoming a big challenge. Many people don't understand. I mean, I really would like to appreciate and thank all my team members who do all the hard work. Just like not only us, I mean, all other MPI stacks are doing very similar things. So it is becoming like a the Formula 1 race car. You need to match the driver. I mean, who is the driver, who is in the driving seat, how he or she drives. You need to exactly match so that you get the best performance. Running application is easy, but squeezing each and every cycle, lot of tuning is needed. We have the capabilities. So I tell everybody saying, okay, give us 3 months of your machine. We will give you the best MPI, but nobody wants to give that 3 months of machine, because you have to run from all different sizes. I mean, cores are becoming larger. Some people want to run like a all MPI, some people want to run MPI plus OpenMP, 2 ppn, 4 ppn, and the biggest beast components are the collectives. Broadcast, I mean, there are 15 algorithms or 18 algorithms. How do you optimize for all different ppn, all different system sizes, all different topologies? It is becoming really challenging. So I'll try to illustrate some of these things in my talk, but I just want to tell that, and that also happens. I mean, Dan knows. I mean, while the machines are coming, hardware is changing, software is changing, firmware is changing. You get 4 hours. We quickly run something and give a version to RPM. So for last 3 months, I think we have been working very closely with tech folks. Every few days, we give a newer version. I'm sure they are trying to use a newer firmware, a newer software, a newer driver, everything. So it's a I don't know whether there will be any end to it, but this is becoming bigger and bigger challenges. So I just want to indicate that. So with this, let me give a little bit of overview of where we stand in the MVAPICH project, latest status, and then the future roadmaps. So as many of you know, I mean, so we are in a exciting, these are like the XScale things from the top 500 I have taken here. I mean, if you see in the 2017, we crossed 100 petaflops. Now in the 2018 or the 19 here, it's the 143 petaflops, which is the summit. But of course, the bigger issue is to go into the 2020 and 21 for the exaflop. And so again, somewhere, I mean, we are already in like in the 2019 second half. So we'll see in 1 or 2 years, some machine somewhere in the world will be coming out to beat these exaflop. So then the question is, how do we design software stacks for these kind of machines? So our approach has been like this. We always start with the programming models. Then I indicate these are like my supply side. Like for example, we have different architectures, accelerators, networking technologies, and we need to deliver the performance. So then the question is, how do we bridge the gap? So this has been our focus, especially in my group and the MVAPICH project, to design this kind of a communication library either in a layered manner, or also we want to go into a co-design manner to give the best performance from all these technologies and to the top. So obviously, these are the kind of the very broad challenges you see. I call it like MPI plus X, like MPI or PGAS or OpenMP. A lot of combinations are taking place. Of course, you need to design very good performance like protocols, internode, intranode, scalable job startup. I'll be talking about a little bit. Then the low memory footprint. This is also becoming a big challenge. Even though you see that number of cores are increasing, the amount of memory per node is increasing. If you do a quick math, the amount of memory per core is decreasing. So then the challenge is, how do you design a runtime? I can give you a very good runtime and tell you that, look, I take 70% of your memory. you will not be happy. Okay? But the question is, if I tell you, oh, I can give you the performance, but only 30% of your memory, you will be very happy. But how do you design those kind of things? So that also becomes a big challenge. And then I talked about this collective. This is a beast itself. Blocking, non-blocking, all different collectives, all different ways. How do you optimize? And then how do you balance intra-node and inter-node communication? These days you see like more and more number of cores are coming. If you see the ROM architecture, I mean, it's 128 cores. Just put 8 of these, you have a 1,000 core system. So a lot of communications are happening within the node. So we have to keep on optimizing within the node communication, intra-node communication, both point-to-point and collectives. Then of course, efficient multi-threading, then these accelerators, fault tolerance, QoS. So like this, the list keeps on growing. So in this context, we started this MVAPICH project almost the day one of InfiniBand. Prior to that, in my group, we are working on Myrinet, Quadrix, all those IBM SP. And when InfiniBand was the very first one got announced in October 2000, we were the very first ones to jump in. And in fact, we had the first, if some of you remember, like a supercomputing 2002, we had the first demo of our open source thing, and I remember it was running on 8 nodes, and it was not stable. Okay, people were coming and saying, "Oh, 8-node InfiniBand MPI is running." The latency was what I remember. I think it was 10 microsecond or something, but it was running. Okay, so that, and now from 8 nodes to we see Frontera is 8,000 nodes. Things are running. So we have been working in the community over the years with this technology. I'm very proud of my team. We are now 18 years of this project. We started with the basic MVAPICH, which was MPA 1, but we have been expanding a lot of different versions. I'll talk about that. So currently it's being used by more than 3,000 organizations, and these are again based on voluntary registration. A lot of people just download, they don't want to indicate themselves, that's okay. Last supercomputing, we crossed 500,000 download just from our website. But of course, it's a part of a lot of other vendor stacks, OpenHPC, SPAC, all those things. We don't keep track, but this is just from our OSU website. So depending on the time frame over the week, we see several thousands downloads every week kind of things. And not only that, I mean, these are the largest systems which are using, and we work closely just like with Frontera. So this is just like a timeline. If some of you remember, we started with MVAPICH. Many of you might not be knowing why this odd name came. We were a derivative of MPitch, and if Gilad and other people remember, like the very first thing was MVAPI. That was the InfiniBand provides verbs level API. Okay, so we want to put a word so that we give credits to everybody and also tell what is new. So that's how this name was coined. And then it was MPI 1 continued for some time, and then the MPI 2 we introduced the OSU MicroBenchmarks, so we declared the end of line. Then we had this MVAPICH 2X, then we had the GDR, which is the GPU optimized version. Then we had the KNL mic version, again that will go down, systems are going down. Then we have the virtualization for the cloud. We also had an energy aware version, and then this is the integrated network analysis monitoring. So over the years, depending on the different diverse community, we have diversified a little bit to customize different kinds of segments, and towards the end I'll again tell we are trying to again shrink little bit. I'll talk about that in the end. So this is the kind of the download timeline. You see we are in a very sharp rising curve, just in pure terms of downloads and in the release map kind of things. But this is our overall software architecture. And of course, decade back we started with HPC, but now also DL. So we try to combine these both. We keep the objectives both the HPC and DL. So we take care of not only like InfiniBand, but IOR, Procky, Omnipath. Omnipath, as many of you know, just Intel declared that they are not going any further. But also all the different architectures, Intel Xeon, OpenPOWER. We had the mic support, ARM, Nvidia GPUs. But this is where all our inside designs remain. And then at the top level, not only we provide support for MPI, we also support for PGAS, UPC, OpenSMEM. We also have MPI plus PGAS. You can run pure MPI jobs. You can actually mix and match in the same job. Some part can be MPI, some part can be UPC. some part can be MPI, some part can be OpenSMEM. So this is the kind of the broad architecture kind of things. And even though like we are an academia, our objective of course is first to publish papers. I mean, this is what all the students work on. But over the years, I've been very fortunate to have a very nice team. Not only we publish the papers, but 6 to 9 months we can actually take the code and then push it to the public. It requires a lot of like a QA effort. We do very exhaustive unit testing, all different test procedures, different kinds of 19 different benchmarks. So all for every commit, roughly we had estimated we spend 18,000 core hours just to get the stack getting tested. And once the code is stable, we also do a performance regression compared to the previous version, because nobody wants a newer version with slower performance. So we make sure that all the point-to-point collectives, everything, we are not losing anything. Then we do some application-based evaluation. Then we do evaluation on the larger scale systems, like wherever we have access, and then we push it into the release. So we typically, just like any other software stacks, we go through alpha, beta, RC1, RC2. But I just want to indicate that all of these go through this above testing. So our naming is more in terms of features. Like as we go alpha, beta, RC1, RC2, we add most of the features, fine tune, stabilize, but not like that there are bugs in the beta or RC1. So you are welcome to even use any of the earlier version for large applications. So these are like all the kind of libraries we have. So I'll just quickly go over the basic MVAPICH 2 and then gradually go over these. So the basic MVAPICH 2 again targets all these 4 networks: InfiniBand, Omnipath, Ethernet, IWARP, and Rocky. So this is a new release we made just last week. So it has a lot of features. You can take a look at it. But every time what happens, you see like we have support like optimized for Azure, optimized for AMD, EPYC ROM. So as the newer processor architectures come, even the networks come, we spend a lot of time on tuning. So we have some intelligence in the stack. As you build, it automatically detects that, oh, this is the processor, this is the it has so many cores, this is the network. So it internally does a lot of tuning. But the challenge is that we need to have access to those. If nobody gives us access, it is very hard for us to optimize on that platform. Of course, we have some fallback. It detects that, wow, this is Intel, might be not the Cooper Lake, but it will fall back to Cascade Lake, the previous generation kind of things. So we have that kind of an intelligence. So let me just talk a little bit about some of the features and some of the graphs just to give you some highlights. So this is like a MPI latency. This is like a small message latency over the years. We have all the different technologies, the true scale QDR, FDR, dual FDR, EDR, and this is the actual Connect X6 HDR. This is the 200 gigabits per second SDR. So here we see the left hand is the small message latency, half of round trip. So we are around like a 1.11 microsecond here, and in the large message, of course, the bandwidth matters. So the Connect X6 HDR is trying to give you the best performance. So then this is the bandwidth. The left hand side is unidirectional bandwidth. So you can see how over the years the technology has evolved. So this is like the QDR, FDR, EDR. This is HDR. So this is like a 24.5 gigabytes per second. If you do a math times 8, so we are coming close to 200 gigabits per second. We are losing out a little bit, and then this is the bidirectional. We should be getting 50 gigabytes per second, but we are getting around 48. So then every time these machines come, as Dan indicated, many times actually when some large system is being deployed, we get contacted because no MPI stack is running. Okay, the biggest challenge is the MPI is not able to start. Okay, so that's what I call like a job startup problem. Like I think Hari gave a good example yesterday. You might have a Ferrari, but if it doesn't start, I mean, what is the value? Okay, so that's what happens, because think of like 8,000 node with 56 cores like Frontera. It's do a quick math. It's like a 400,000 MPI process need to start. Okay, so over the years we have been putting a lot of intelligence to improve the job startup performance and also reduce the memory requirement. Okay, because in the beginning you have to detect all the connections, you have to have some buffers. There are all different kinds of protocols. So I'll not have time to go over all these things, but these are all available in papers. But let's show some numbers. So this was happened on one TAC Stampede KNL system was coming. Again, this was happening. Intel MPI was shooting up. Then we were able to do MVAPICH to 2.3a. You see here, it's 230,000 processes in 22 seconds. So we can do MPI in it. Okay, and these numbers were also from the Oak Forest packs, the Japan system, and 5.8. So this was while the machines were being deployed. Of course, once we make the code available, all other MPI stacks take the design. Again, Intel MPI has improved over the years also. But this is the latest number. Dan, sorry we couldn't send you the slides. 1 hour difference makes a big thing. Taking the numbers, putting it into the slides. So this is where just on the Frontera, this is like up to 1,000 nodes, 57,000 processes. So see here, 3.9 seconds we can do MPI in it. Just count 1, 2, 3, 4. 57,000 processes have started. Intel MPI has improved, but still there is a gap here. And how it happened? So this is what again to Dan and his team. So you see, this was the previous version, and as soon as we got machine access, this is the number we are seeing, the green thing, and we say, oh, that is not right. And then we are able to optimize, and I think Hari, what 3 days? 3 days we are able to give you this better number. So we have like dedicated people who knows exactly where to optimize, but the access is the most important. If you get the access, you have to. It's not just that you can theoretically design. It's not a math formula. You need to see what are the cost, how things are being connected, and then we're able to improve and then give them a version. So here you can see like it improves significantly, and that's what is running currently in the version we have given. So this I just want to illustrate like this the startup kind of issues. Of course, the collectives we continuously have been working on. Yesterday you heard from Devender about SARP kind of thing, SARP V2. So we have already integrated that into our stack. In addition, we have done more optimization. So this shows like a average D dot all reduced time in the HPCG. If you even for a very small configuration, you are able to get good performance. Now, in addition to the x86, we are also working with all the other vendors. So this is like the OpenPOWER number. So this is like an intra-node. We are comparing with our Spectrum MPI. So here you see like in a 220 nanoseconds. This is where the designs are coming. These are intra-node communication. Is no longer in the microsecond. We have to go into the nanosecond range to give you very good performance. We are also working with ARM. Of course, they have all different versions. So this is in Cortex A72. Again, similarly, like in a 270 nanosecond, we are able to do MPI level communication between core to core in the same socket. Now, we also have been, as the things are becoming more complicated. So this is the project actually we have started with Samir. He will talk more on this with the tau. The whole idea is that over the years you would have seen the MPI has been a black box. Okay, so when you try to see where time is being spent, there has not been any effort. You can do profiling and all, saying this much time is going, but really internal to the MPI stack, saying which call or where you are spending time or how much memory is being put. So MPI 3.1 introduced this standard called MPI-T. How many of you are familiar? MPI-T. So we have taken that approach and then trying to make that black box to white box. So the whole idea is that this MPI-T, while the job is running, it can give you a lot of performance variables. If you trigger them properly, it gives to the upper level application or tool saying this is what is happening, and you can do the analysis and then do a control variable, push it, okay, to change the dynamics of the MPI library. So we have been working closely with Samir. I think he will go through the more details in his talk today before lunch. But think of at a high level, this is what I have told Dan and also the NSA people in the Frontera project, what we want to do. Think of like all of you must have heard of personalized medicine, right? We want to do personalized MPI library. Okay? So through this PVAR and CVAR, we want to, per application, per platform, we want to optimize, and it can be done automatically, okay, through this PVAR. So it will try to run, it will find out like if you run the application once or twice, you get the insight and then do the analysis, change the control variables. That is our goal for the Frontera. So might be 5 years down the road in the 12th mug meeting, I'll report where we are. Okay, but that is the kind of the goal, and we want to do that with Frontera. Scalability is of course important. I mean, these are like the Stampede 2 numbers, all the different things. As you can see, we are able to scale into 8,000 nodes, 4,000 nodes kind of things very easily. Frontera, of course, it will take us another few months to optimize the stack again, because the system is being stable. We have to run more experiments. So then last week, some of you must, if you are on our mailing list, would have seen we made a release for MVAPICH to Azure. So it is a one-click deployment kind of things. Jitin he will be talking more in his talk today. So here are some numbers. We compared with MVAPICH to X and then HPC X here. So you can see on like a even like the 8 nodes kind of things, we are able to deliver better performance. This is the performance of Radix. This is the performance of FDS kind of things. So as we go forward, these are our like the upcoming features for the MVAPICH 2, integration of the SAR2 and associated collective optimization, and all these are platforms you are coming up. Intel Cooper Lake, AMD Rome, ARM. So we are trying to do a lot of optimizations on those platforms, and also we are trying to go into a next phase in the design, dynamic and adaptive communication protocol. So this paper actually got a best paper award at ISC 17. Hari is the lead author. So the broad idea at a very high level, if I want to tell, many of you know the MPI. There is an eager protocol, rendezvous protocol. Okay, most of the time you have a threshold, but that threshold, it's for all pairs of communication. You cannot do per pair. Okay, but here in this design, we are able to achieve that per pair, because many times when you are running the application, it's not that everybody is communicating uniformly with everybody. So we want to introduce this new per pair you can adjust. Okay, if we can do that, that is the kind of you get the dynamic and adaptive, good overlap, optimal memory requirement, the high productivity, high performance. So we have the paper and the prototype design. We need to take it into the production code base and trying to push it. So that is the MVAPICH 2. So then let me talk about the MVAPICH 2X and then the MVAPICH 2X AWS. We also made a release for the AWS. So this is the broad, again, the similar kind of architecture. We started with the MPI plus X paradigm, but now we have a lot of advanced designs have gone in. So this is the latest release we did March 2019. We are trying to make a GA release before Mug, but we couldn't do it. Might be wait for one more week. We'll be having the GA release of this MVAPICH 2X. So here we are providing a lot of features. Okay, so here there is a basic version, there is a basic XP mem. I'll talk about a little bit this intermediate and advanced, which has a lot of this UMR, ODP. So we are trying to make it a little bit separate, because some users are just generic users. Some users are very advanced users. They want to experiment. So we are trying to enable the community in all the spectrum. So depending on what they want to achieve, they should be able to achieve that. So here I'll try to show you some quickly some of the features of the MVAPICH 2X. So the first one is the direct connect transport. So that is from Mellanox instead of the RC, which is a reliable connection. So the DC allows you to really scale, and we are actually testing that on Frontera. I think things still there is some bug we are trying to resolve. It runs up to certain sizes and then beyond doesn't run. But that is the whole idea here. If you see, if you compare to like RC, this is the green, which is the DC. You can reduce the memory requirement, connection managed memory requirement significantly. You will also get performance. So that is the kind of the scalable protocol we want to use. So in fact, this helps. This is like we are working with Pramod at the EPFL, the Blue Brain project. So here you will see even sometimes using this DC at scale, you can actually improve even 39%, 76% kind of things in the execution time. This is a new protocol we have introduced. It's already available in the MVAPICH 2X RC2. This got even a best paper award at SC 2018. It's called Cooperative Rendezvous Protocol. So let me explain this at a high level. So the whole idea is, let's say I have a friend in Cincinnati. I want to give a package. So either I drive to Cincinnati or my friend drives to Columbus. Okay. So in this protocol, what we do is, depending on whoever is ready, why don't they start driving? So they meet somewhere in the middle. Okay. so which cuts down the latency by half. Okay. So, if you want to send a message from within the node, so this is like within the node, so that is why we call it like a cooperative protocol. So, if you do this kind of protocol, so you see up to 2x improvement in large message latency and bandwidth, even up through graph 500 at 1536 process, you see 19% improvement. So, we take these kind of novel designs and then trying to improve the MPI stack. I do not think any other MPI stack has this kind of cooperative protocols yet. So, then we have been doing like the SARP together with multiple leaders. So, this was a paper at SC17. So, the whole idea is that many times when you do hierarchical algorithms within the node, you only have one leader, but as the number of cores are increasing, one leader may not be good. So, you may need 2 leaders, 4 leaders depending on the collective operation. So, we call it like a multi-leader, and we have put together that with the SARP. So, here you can see like a for large number of processes, we can get very good performance. This was taken on Stampede 2, 10,000 processes. So, you see up to 32K, we can give you like a 2.4x improvement. Yesterday in the Hari's presentation, we talked about a lot about these collectives, CMA based collectives. So, these are like kernel based support. So, that support is already available. So, here if you see, this was taken on the older system KNL and all. This is in a log scale. So, for very large messages, which a lot of these deep learning applications are trying to use now, we should be able to give very significant benefits in performance with a factor of 2.5, 3.2, etc. So, then we discussed a little bit also yesterday about this asynchronous progress. So, that has always been a challenge in the MPI stack, especially in the Rendezvous. If I want to send you a big message, first I need to send you an RTAS, but then you need to be ready to pick up the RTAS. If you are busy in the computation, then you cannot pick up the RTAS, then we lose the overlap. So, this is the design we have done. This was presented at the EuroMPI and then later on in the Parallel Computing Journal. Here you can see like the P3D, FFT, HPL, etc. We can get up to like a 33%, 29% benefit, and we do not need any additional core. So, there is no oversubscription, we do not need any dedicated core, but we are able to achieve this. So, then we have a lot of support compared to CMA. This is the next the kernel based support called the XP9, and again this is not there on Frontera yet. We have been talking with Frontera people. Once the system is stable, we will try this. Significantly again you get the big benefits compared to the other stacks. This is in again a log scale. This is like OSU already used. You can see 1.8x, 4x kind of improvement. This was presented at the IPDPS 2018. Same thing also happens on other platforms compared to other MPI stack. This is on the OpenPOWER, similar kind of benefits we see. And then if you can improve the collectives, as you know, a lot of these deep learning applications are dependent on that. So, this is like a CNTK AlexNet training. So, here you can see like a 20%, 9%, 15% kind of benefits you see for the deep learning. Even for scientific applications like a mini AMR and all, you can see these on the OpenPOWER, you get 36%, 42% improvement. We also like those are like the reduction based collectives, but you can also see benefits in the non reduction based broadcast, gather kind of things. And sometimes there is also an interplay between the protocol and the collective. So, again here we are working with the EPFL folks. This is a comparison with HP MPI, and Pramod will give more details, and here we are able to give like a almost factor of 5 improvement kind of things. And then of course, the combined PGAS MPI work is already there. This is a little bit older results, but again it has support for OpenSMEM, UPC, hybrid versions. You can mix and match. If you combine MPI and OpenSMEM, you can see like a factor of 13x improvement. Even SOT, you can get 51% improvement kind of things. So, then recently we took that MVAPICH to X and had a version for AWS, and AWS actually many of you know, they have a different adapter. It is not InfiniBand adapter, they call it the Elastic Fabric adapter, EFA. So, we worked with them that has some UD support, but there is a newer protocol they have introduced, Scalable Reliable Datagram, SRD. So, we had our design based on that SRD, and here you can see like these are some point to point large message latency. So, this is the green is our new design, we are able to improve significantly on the latency, the bandwidth, collectives, similar kind of things, and all reduce also similar kind of improvement. These are the applications, and compared to, so they have the I think yesterday there was a question, Santham. So this is their installed version. So compared to that, we see this is like a even on like a 8 nodes, we can give you like a 10%, 25% better application level performance. So this has been released. It has not gone into their module. We are working with them, but currently, if you just follow our website, there is a very nice script you can download. As long as you have an AWS account, you should be able to download and run and exactly get the same performance kind of things. So then, while the next phase, what we are working on the MVAPICH like the XP9 based derived data type, a lot of these scientific applications actually use derived data type, and also the hardware tag matching. So I'll try to show some numbers. So this is the MPI data types together with XP9. We have done this design, and again, you see a significant benefits. If you see the number of these, like a 3D stencil, milk data type, NAS-MG data type. So we'll be trying to push this into the next release. And the hardware tag matching. So this is the support Mellanox has on their adapter. So we have been working with them, trying to exploit that thing. The tag matching also has some limitations, but we have tried to expand that. And then here it says like let's say the issue latency. Here you will get around like a 35% improvement in latency of small and medium messages. These are like a non-blocking collectives. You get almost 1.7 and 1.8x improvement. So those are the kind of on our roadmap. We'll be pushing that. So then let me move into this version, which is very highly optimized for GPU. That's what we have been working on for the last 4 or 5 years. So this is the concept. We started, in fact, ISC 11 paper. In fact, Santhan is there. He was there in the team. He was the lead author. Called CUDA aware MPI. So how many of you have heard of that? CUDA aware MPI, many of you. So the idea is that if you take a look at this kind of like a GPU and a network, many times people just do a CUDA mem copy, do MPI send, MPI receive. Those are high productivity, but performance is not good. Sometimes you do pipeline, but you need to spend a lot of time. So what we introduced, this concept like CUDA aware MPI, if you know how to program from host memory, you just say MPI send from the device buffer, MPI receive from the device buffer. That's all you need to do. Everything else, the MPI library takes care. So I'll show you the animation. So the end user even doesn't need to know CUDA, doesn't need to know how much time is being spent where, and it will give you the high productivity and high performance. So once we had this design and the subsequent papers, Nvidia approached us, and then we had a lot of detailed collaboration work with them. So since MVAPICH to GDR 1.8 to 232, all these not only the basic concepts but all advanced concepts have been used. So we just made a new release. Again, in the last week, we made a lot of releases last week before MUG. So we have optimized a lot of this MPI already used for different platforms, including DGX2. In fact, on the summit, we have run it, the scale all reduced to 24,000 GPUs. That is the largest summit we have run and optimized already used. So if you have any summit account, just use this version. You should be able to get very good performance. Now, here is the number I show. I think yesterday even Devinder also showed some of these numbers. So this is the number 1.85 microsecond. You can send from data from GPU to GPU in another node over the network. Okay. So this is a very impressive number. If you see host to host is around 1 microsecond, another 800 nanoseconds we are able to send this. The similar kind of designs also we have taken. So this is the NVIDIA link to Volta. Of course, yesterday also we talked, this doesn't have the GDR copy yet. So that's how we are getting 5.36. If some 8 people install GDR copy, we'll be able to give you similar kind of 1.85 microsecond, and then within the node we are able to saturate here up to 70 gigabytes per second. So then the benefits, you see, like this is a Humdi Blue molecular dynamics application. You can see we can improve the performance by a factor of 2x. This is our flagship project. In fact, we have been working closely with Switzerland Supercomputing Center for the last 3 years. If you have been in the Switzerland, and open up your iPhone to see the weather, we are actually driving that weather forecasting. So there is a machine in the CSCS, and we are supplying the MVAPICH to GDR, and then the partner is Meteo Suisse. So they are running their weather forecasting application, and we are trying to deliver the best performance there. So then on the GPU side, as many of you know, I mean the field is moving into the deep learning. These are kind of like a scale up, scale out people have been working on. So of course there are different solutions, nickel, nickel 2. We are trying to push through our MPI stack. How do you get the best DL performance? So here is a paper we published recently at the CC Grid 19 a few months back. So broadly, if you see these two curves, the very extreme right is the yellow is the ideal, and we are able to get very close to that, almost 90% of the time. And then I think yesterday also we discussed like there is a nickel 2 from Nvidia, the library, and through MPI again, if you properly do all the tuning and all, so this is on the compared to nickel 2, we are able to deliver almost 3x better performance and around 1.2x for large system. This is on DGX2. We can actually give you even better all reduced performance compared to nickel 2. So if you are running any DL applications using nickel 2, just change to MVAPICH to GDR and you will see better performance. Here we have done again on the summit. So this is again on 1536 GPUs. So this is compared to the nickel 2 again, the latest version 2.4. So here you can see like we are able to give you almost 1.7x better performance or 1.6 better performance here, and these are compared to even the other API stacks, and even sometimes we are not able to run also with the other API stacks. So it's not the basic performance, even efficiency is also good. Here we are able to get like a 9% higher performance on the DGX2, and this is one of the largest things we have run, ImageNet 1K. So it has 1.2 million images, and so we are able to run it on Summit with 1536 Volta GPUs, and we are able to reach around 0.35 million images per second. Okay, and these are again yesterday we had some discussion. So based on these kind of things, what we see like the total time, we should be able to achieve this in like a 5.5 minutes kind of things. So as we are like this GPU version, we are continuously again enhancing. So currently what is happening is MVAPICH to X and MVAPICH to GDR, these two are separate code base. So now we are trying to integrate them back. So to bring both the benefits of the host side as well as the GPU side. It will take us a little bit of time because this code got bifurcated, and bringing it back always, those of you know the merge issues. There are a lot of issues, but we are trying to resolve. So you can have now a single package which will give you the best host based, all these derived data type, XPMM. We are also trying to provide support for SARP from the GPU buffers. And in addition to TensorFlow, we have also expanded to PyTorch, MXNet. Those are the next networks which are coming, and we are trying to optimize. So these are some numbers based on our already optimized designs. This is like OpenPOWER. You can see like a scalable host based collectives. We can improve by a factor of 5 and 3. I talked about the CSCS, that Meteo Suisse application uses a lot of data types. So we have actually improved, but it has not pushed. We can improve in factor by 15. By factor of 3.4x. So we have data type designs in the kernel itself. Okay, so instead of most of the time people do the GPU does the computation, you bring the data to the host to do the packing, unpacking, and send it out. So instead of that, we have now algorithm which can actually do all the packing, everything within the GPU and send the data out. So we can get the best performance. So those are the kind of our roadmap. Then let me briefly touch about this network analysis and monitoring and the OMB. So this is a project going on for several years. So what we are trying to do is trying to integrate the entire stack from the top to the bottom, because there are many tools where you can see sysadmins can look at the network. Okay, but network, when you see the analysis or the traffic, it is independent of your job. So what we have done here is actually, if you see here, like this is actually a SDSC cluster Comet. you can see the topology. Just like freeways, you can see which link is getting heavily loaded in colored form, green, yellow. But more importantly, what happens is you can drill down from your console. The end user can actually see, okay, give my job ID. From that job ID, you can see what is happening, how the collective traffics are going on the network, how the point-to-point traffics are going, where the contentions are happening. So in fact, there is we are working very closely with OSC and Dr. Karen Tomko and Hee Chang. I think they will show some of the things tomorrow. Is a talk and demo is there. We have been running, I think, for last several months, all different versions. We get feedback and continuously update, and then so we are trying to stabilize the next release. Once things run in a production manner at OSC, then we'll be trying to push the release. That is our goal. So then, of course, the issue MicroBenchmarks, I think Dan touched base on that. I mean, so this we started from the very day one of our project. People didn't know how to measure MPI performance. People knew how to measure the application level performance, but not MPI performance. So over the years, continuously, not only MPI and the PGAS, every time we add a feature, we have a corresponding MicroBenchmark so that people can measure, compare different stacks. This has also become nowadays a procurement line items for a lot of procurement suites and acceptance test. So we also, over the years, we have also tried to do a compilation of best practices. So if you go to this page, whatever we know, we also take input from others and give credits. Anybody can contribute, I think, saying, look, on this platform, we have run MVAPICH 2 with these parameters, because MPI stack, there are almost like 500, 600 parameters you can move around. So we don't want the effort to be wasted. If somebody in the world has done some work, some optimization, if they can share with us, we will put it here with credit, then others can actually look at it and then do exactly the same things. So this is the new initiative we have started. So with this, let me try to conclude here. So just like any other stacks, we are trying to also head into the exascale. In my overview, I showed you that the top systems which are running at the number 3 onwards, but actually MVAPICH 2 is running on Summit and Sierra, but I cannot officially claim because there are some legal issues with IBM, Spectrum API and all. So once that get resolved, but as you said, we have run it on 22,000 GPUs. You can download our stack and run. A lot of people are running it on Summit and Sierra. So we are trying to capture like 1, 2, 3, 5. Okay. So we want to catch all top 10. That is our goal as we move forward. So we are continuously working on newer features like MPI plus task, tag matching, adapter memory, Intel Optane. I think once the Frontera thing is there, we'll try to do some things. Bluefield, we have started talking with Gilad and Mellanox. They have this adapter with Bluefield programmable things. So we are trying to explore some of the things to offload there. Also the CAPI, GenG, a lot of those new interfaces are coming. So those are our broad goal. Now, before finishing, I also want to indicate, I mentioned about this last year, and I think Dan indicated. So now we have actually a commercial offshoot also, because many people, we have been supporting it in an open source manner, but many organizations want it actually in an official documented contract form to take care of platform specific optimization, tuning, timely response, all kinds of things with different service level agreements. So we have this offshoot called XScale Solutions. So in fact, through this, for last 2 years, we have been trying to provide very nice support to Lawrence Livermore National Lab. If some of you know, Adam has been coming here. This year he couldn't come. Now he is here from Livermore. So we have been continuously working not only on the MPI stacks, we have been able to address their application level issues also. Sometimes on very large scale things break, you don't get good performance. We are able to provide support to their system, sysadmins as well as the application people. And we are also working with the L-band team, that is their deep learning thing. So we are expanding on that. So in fact, we are also working with the IBM OpenPOWER consortium here. This organization is a part of the Silver ISP member. As I was telling, This OpenPOWER North America Summit is taking place yesterday and today. In fact, yesterday we introduced 2 products by combining packages. So now you have an XScale HPC and XScale AI product. So this XScale AI product, for example, combines MVAPICH, Horobot, TensorFlow, everything together. So with a one click, you can do the deployment. So those of you who are interested, please feel free to send an email. So we are trying to engage with not only in the basic communities, also for the commercial organizations and all. So with this, let me thanks to all our sponsors here. Without their help, we couldn't sustain this project for like 18 years. But more importantly, these are all the heroes. Where we are, these are all the past students and staff. In fact, some of them are sitting here. Might be I'll ask to raise hands. Santhan, Jitin, Devinder, right? So these guys actually, they have gone to other organizations, but if you go down the code, these are the guys who have written many parts of the code and many parts of the paper. So if you look at some of this list here, you will see all these guys have gone here and then been working at all different places, and still we are working together, kind of things. So with this, let me stop here. If there are any quick questions, I'll be happy to answer. I know I have 8 and 10 minutes to the break time, but we'll try to recover.